Welcome, Paleopedologists. Today, the last of the 5 soil-forming factors, and it's an important one that actually employs people in paleopedology, but we'll get to that in a bit. It's the factor of time. Oh, this pen is so much better. I like it. The idea for time is that we should be able to have a chrono sequence, and that will lead to a chrono function. That we should be able to get a mathematical relationship between some feature of the soil and the time over which it formed. We could also do an experiment, I suppose. It would just take a long time because the times involved are many thousands of years. Experiments have been done. They've been done with spertosols. And they take a long time. If you take a column of sand and you have pine needles here, in 10 or 20 years, what will happen? Well, you'll start to get a BS horizon and an E horizon. This is leached, and this is spodic, meaning that it has been cemented with iron and with organic matter. To form a spotosol, or what they used to be called podsols, will take about 100 years at least to form a decent one, but you can sort of see traces of it after about 30 years. That's not really a good option for studying or gaining chrono functions. A better option is to use place for time, to go into the landscape and find places where the landscape is of different ages. The classic landscape for that, of course, is where glaciers have been retreating. So here's the glacier, and it's laying down till. And the till of previous glacial advances are further away from the glacial front. Pretty typically, this is about 6,000 years old. This is about 8,000 years old. This is about 12,000 years old. This would be the maximum extent of the glacier from retreating from the last ice age, and then there's been a kind of a continuous retreat since then, and we can study the soils on these radiocarbon dated surfaces, getting thicker and thicker and better developed with time of exposure. This is a good chrono sequence because it's in a relatively small area. This is just 10, 12 kilometers or so. The same climate, same vegetation. Well, not quite the same vegetation because here there'll be small trees, and then the trees will be getting bigger when you get out here, and be pretty big when you get out here. So vegetation is not that different, but comparable, not amazingly different. The relief is generally relatively low, and the parent material is relatively uniform. If this is glacial till, it's basically a ground up mix of rocks in the bedrock. Another place to study these sorts of things is in alluvial terraces, such as we have here in the Willamette Valley. In the Willamette Valley, we have these terraces which form these flat surfaces with rises. Here's the Willamette River meandering down through the middle here. These surfaces represent ancient surfaces in the uplift of the landscape in a 4-arc basin. In our part of the world, this is gently dipping Eugene Formation sandstone. And what's happened is that the Willamette River is incising its way down through this bedrock. The soils that are nearest the stream are the youngest. They are something like 2 Ka in age. The soils up here are quite a bit older, something like 8 Ka. The soils up here are older again, something like 12 Ka. And the Willamette Valley wasn't glaciated, so these surfaces up here have very thick soils, which are great for growing wine, by the way. And these are something like 40 Ka, 40,000 years old. We have a relatively limited area. Pretty similar vegetation. Up here you tend to get the Douglas fir. Here it's kind of an oak savanna, a grassy vegetation, both down by the river and on these low terraces. The parent material is fairly uniform. Let's imagine this is just Eugene Formation. Sandstones of late Eocene age, from when the whole Willamette Valley was inundated by the sea about 30 million years ago. These are good places to look at the relative age of soils in a small area, good chrono sequences, and from them we hope to get a chrono function. So if this is time on this axis, and this is a property of the soil, let's imagine it's clay content or color. The ideal would be that there's a straight up relationship. So if you have percent clay here, and you have another soil, you can then infer that amount of time. This would be an ideal chronofunction. Now, why we make a chronofunction is because radiocarbon dating is expensive. So we radiocarbon date some of these soils, and we get these ages, and then we measure the soil property. We develop the chronofunction. But once we have the chronofunction, when we find another soil in the same area, we can date it by its soil properties alone. This is why we do a chronofunction. It enables us to extrapolate the few radiocarbon ages that we have to understand other soils. This can be very, very useful for a variety of purposes. For example, making an investigation of the location of a nuclear power plant or a dam. We want to know the age of the soil, and we want to know how that soil may have been affected by uplift, by tectonic activity. You don't want a dam or a nuclear power plant on an active fault, for example. These considerations mean that quite a number of consulting geologists are employed making chronofunctions. There are problems, however. This is the ideal. In some cases, we have what can be regarded as a steady state. Sometimes the soil features can develop to a point where they are done. There's just no more development is possible. All the feldspar is gone, so you can't make any more clay. That's unfortunate. That means the chronofunction is only good for this interval here. In other cases, a development of a feature may form rapidly during one phase and then taper off. This is what's called a threshold. is a possibility also for the development of clay horizons. You can imagine a situation where the clay is forming, a BT horizon is forming, but then the whole thing has to be really plugged up before it can form rapidly and form more clay. And then there's not much feldspar left after that, and there's no more clay to be had. Threshold effects, steady state effects, these are a problem for chronosequences. However, people are finding, now that we have more accurate dating, not only radiocarbon but also beryllium dating and other surface dating, that a lot of these chronosequences give pretty close to ideal chrono functions. Now I'll go through some actual quantitative chrono functions in a bit. Let me though outline a very simple scale, which is really worth considering in terms of a soil development. So qualitative. Qualitative soil development is actually a feature of all soil taxonomies, really. And it proceeds on three tracks. Quantitative soil development is an idea of the relative stages in soil development, like youth, middle age, and then senility in human scales. In the calcic track, which is one of the best studied, we start out with very weak development. That would be a material that has bedding and other indications of apparent material, but no real accumulation of calcium carbonate. In weak development, we start to get threads of carbonate. In moderate development, we get nodules. Nodules like little potatoes growing in the soil, usually at a set distance below the surface, depending on the climate, deeper and wetter climates, of course. And this is will actually qualify as a calcic horizon. With enough carbonate enrichment for it to be calcic. In strong development, the nodules grow and they become a bench. They grow and coalesce, so we get a bench. And then in very strong development, we have the bench starts to break up. It tends to be broken up by roots, breccias, and then there can be lamina additions of carbonate. We find breccia. We can see that when we have very strong development, the bench is starting to get broken. Now, in this scheme of things, moderate development is pretty much post-glacial. So moderate development is about 5 to 10 Ka in time. This is greater than 15,000 years. This can be greater than 1,000,000 years. This is just 100 to 2,000 years, and this is just 10 to 100 years or so. These are, now we peg the moderate development to a post-glacial soil because that's the most common sort of soil that we have here in the U.S. In the U.S., of course, the glaciers went away only about 12,000 years ago, and most of the U.S. surface soils have been developing since that time. So that's kind of our standard, a moderately developed soil. When we have a weakly developed soil, it's about half of that, and then this is one that's just born yesterday, one that's very, very weak. More strongly developed soils we find in places that escaped glaciation, that are remnants from a southern latitude or a lowland environment where the glaciers never went. Many places in California, Arizona, Florida, Georgia, Mississippi have these kinds of soils. But if you're dealing with most of the Midwest and most of the East, we have these kinds of soils. Actually, this calcic track is not found too much in the East. What's found mainly in the East, in a humid climate, so the calcic is in a dry climate, we have a clay track as well, which is found in a humid climate. In a humid climate, we start out 100 to 10 years or so with roots just penetrating, growing in an undifferentiated sediment. When we have a very weak soil, we have bedding remaining at the bottom, but then there's the development of clay skins. It's got a weak structure. These start to pile up after a while, so that you get quite a nicely developed BT horizon. About 10% more clay, and this qualifies as an argillic horizon. Once again, the argillic horizons are post-glacial soils throughout. We're talking mainly about the eastern U.S. now. These are mainly in the western U.S. What happens after that, when you get to greater than glacial age, is that the BT horizon becomes thicker and thicker, and in the coastal plain of the southeastern part of the United States, some of these things can be. So this is generally about 1 meter. This is generally about 2 meters before you get to the, and these can be 4 meters or so in tropical or subtropical regions, soils that have developed for a long, long period of time. Very weak, weak, moderate, strong, very strong. These are nice qualitative stages that you can see quite easily in a soil profile, in a paleosoil profile, and in a modern one. And then finally, there's the histic or peaty soil, which forms a little bit different from most others. In a histic soil, of course, what happens is the peat forms in the surface. And the peat is forming like a sediment. It is forming more through time. It's a delicate balance between the trees that are producing this stuff and the subsidence of the soil, so that it can actually be preserved as a peat. A moderately developed peaty soil with what qualifies as a histic epipedon is 40 centimeters thick. That's 40 centimeters of peat. So they just get thicker and thicker through time. There are some incredibly thick coals and incredibly thick peaty soils as well, which can be meters thick. This 40 centimeters is taken as the definition of a histosol and the definition of a histic epipedon. and is pretty typical for a post-glacial soil at the northern margins of the subtropical region of the U.S. These are thicknesses of peats. Now, the reason that we can estimate time from these is it's been estimated that peats accumulate at 0.5 to 1 millimeters per year. And that's because peats, woody peats anyway, are from trees. Trees need to respire at the root, so that if the subsidence rate is greater than a millimeter, that means the tree will be underwater and the whole thing will go anoxic and it will die. If the subsidence rate is less than a half a millimeter, that means that all the stuff that falls out of the tree in 1 year is going to be decayed at the aerobically at the surface before the next year rolls around, and so you don't accumulate a peat at all. How this works out is that I just do an order of magnitude difference. So this is 0 to 4 centimeters in terms of the peat. This is 4 to 40 centimeters. This is 40 centimeters to 4 meters. This is 4 to 40 meters. And this is greater than 40 meters. What this means in terms of time is 0 to 80 years. This is, 400 to 8,000 years. This is 8,000 to 80,000. And this is greater than 80,000. So this is 80 to 400 years. We can actually get the time of formation of a histosol from, if it's a woody one. If it's a herbaceous one, like from a marsh or a fen, then all bets are off, because this rate of subsidence only works for woody plants. Now, most coals in the fossil record are woody, and we can see that from the coal balls, which preserve the fossil wood of the plants that made them really quite beautifully. We can also look in thin section to look at elements of the thin section called vitrinite. Vitrinite is a maceral of wood, very common in coals. And fusinite, I've talked about this too. Fusinite is fossil charcoal, which is found in coals because even in places like the Florida Everglades, there occasionally is a fire that burns and incompletely combusts the fossil wood. So this is a nice sort of qualitative scale that we can use for figuring out the time for formation of soils and paleosols. It's a scale that has come from the experience of soil judges and soil mappers, and it is scaled, of course, to North American experience, the rhythm of soil renewal and destruction that is created by the ice ages. Now, there are actually quite a number of really nice chronofunctions out there. One I particularly like is by Mike Machette, 1985. And what he looked at was age in years times 10 to the third, so thousands of years. And he actually took a pretty long time scale. Well, let's see, 150 to 100. And he looked at grams per centimeter squared at the surface of CaCO3. And the scale here was 100 and 200. So what he was looking at was just a cubic centimeter sort of surface of the soil. How much carbonate is in that cubic centimeter of soil through time? And he had quite a number of soils that were relatively young, and then a few really old ones, like at Mormon Mesa, and he found a really nice relationship between the two. He found that it varied a little bit, but not incredibly actually, between different locations. This was Albuquerque, New Mexico. This was Santa Casia. And this was Las Cruces. These were relatively dry climates, of course. We're accumulating carbonate at a fairly steady rate. Another comparable chronofunction is Birkeland. Who was looking at the clay accumulation in soils. This is grams per cubic centimeter of soil, per square centimeter, I should say, of soil surface of clay in the profile. So you can imagine that square centimeter at the surface of the soil. How much more clay was produced in that profile over the whole solum thickness. He did it to a log scale, and he had age in years times 10 to the third, so thousands now. Some of these soils were pretty old, and the best database was in the coastal plain of the Carolinas, North and South Carolina, and of Georgia. He found that they formed a nice linear array in here. These are the ones that Marbut called pedalphas. These are the non-calcareous soils of humid climates. He also found that pedicels were forming an array like this. Pedicels are basically these ones above, the Machette soils that have carbonate in the profile. They're also forming clay, but they're forming it rather more slowly, and so are not such accurate chronofunctions for judging the age of the soil from the amount of clay in the subsurface. So these are two chronofunctions that were developed for particular reasons. This one here for basically New Mexico, this one here for South Carolina, this one here for New Mexico. These are examples of chronofunctions that have been published. For consulting chronofunction work, the sort of work that you might do as a consulting geologist working for an engineering company, you would do your own rather more detailed study for a particular location, which is of interest for the construction that is being planned. Now, so those are two things you can use. You can use the amount of clay, the amount of carbonate. Nodule size is a good one. That's one that I published on that turns out to be a fairly easy one to use. There are other things you can use as well. You can look at mineral weathering. If you look at, for example, feldspar grains, they vary from being fresh, where you can see the angle, the crystal faces, to pitted, to etched to islands. In thin section, you can see this progression of weatherable minerals. It's best if you use something like pyroxene or hornblende, which is relatively easily weathered, but you can quantify the amount of these grains in these different 4 categories and figure out a chronofunction for that. Weathering rinds have also been used. Now, provided you take the same boulder and you don't go from andesite to basalt to granite, generally speaking, with the passage of time, the weathering rind, that reddish weathering rind around, say, an andesite boulder in a till, will increase in its thickness through time. You can't compare a basalt or a granite. We talked about this before. They have different thicknesses of weathering rinds. Steve Coleman did a nice job on this, looking at andesite weathering rind in soils on tills in the Sierra Nevada. You need to get a pair of calipers to do this because they only get up to about 2 millimeters. He had tills of various ages in thousands of years. He found that they formed a nice array. There was a little bit of a difference between different areas, but they were actually pretty close. This is Mount Rainier, Mount Lassen, and this is near Truckee, which is in Nevada, not too far from Reno. These are chronofunctions that you can get from weathering rind thickness if you have paleosalts developed on conglomerates, which actually does sometimes happen. I've seen it myself. Now, some people have thought we need to have something that's more accurate and more reliable. And one notable attempt to try to get something that's a little bit more comprehensive and universal was Jennifer Harden and her Soil Development Index. Or, of course, we need an acronym, SDI. Her idea, which is an interesting one, and came out of the frustration people were having with some of these things sort of turning over, some of them showing threshold behavior, and some of them being generally unreliable. Her idea was to combine a whole bunch of things. Let's have redness. That would be just hue from the Munsell color chart, by which we mean reddish, brownish, purplish. Total texture. That would be clay. Clay film abundance. Structure. We're talking now blocky, crumb, prismatic, whatever. You can rank these. Dry consistence. How hard is it to just crush it in your hands? Moist consistence. Darkness. And that's from organic material generally. The dark color comes from organic material. And then finally, pH, just a straight up measure of pH. And what she found was actually pretty nice. These things that individually didn't behave themselves. So you have a measure of each of these things, and you average them all together, and you get this soil development index, and it has a good range to it. For Southern California, particularly in the San Joaquin Valley, near Merced. This is years. She found it was pretty well behaved. There were ranges that she had in her data, but a pretty nice envelope. Soil development works actually quite well. And this soil development index is still used for engineering purposes in the San Joaquin Valley of Southern California. Quite useful. For paleosols, not so good. pH is a problem. As soon as the soil is buried, the pH goes wonky. We lose most of our organic matter to burial decomposition. Moist consistence and dry consistence, not too meaningful because it's now a rock. So we're just left with half of the values. Nobody's really tried it with soils, something like this, but I think it's kind of a useful and productive way of looking at soil development with paleosols as well. So we have a variety of qualitative and quantitative ways of looking at the age of a soil. What else is of interest when we're talking about the age of soil? Well, what's really of interest to people who are into sedimentology is the rate of sediment accumulation and what is called sequence stratigraphy. Now, when I do a log of paleosols, I do it as if I were a sedimentologist. We do a grain size scale. So that here we have, say, a paleochannel with gravel, and then this is silt. This is clay. This is sand. This is gravel. I reserve this one for coal right here, if there's coal. So I don't get that far down, however. And then here's another paleochannel here. Paleochannel goes up to here. And then we have a sequence of paleosols, like so. These are trough crossbeds, sandstone, gravel. This is sandstone here, and then we've got clay here. This is a sequence of soils which is weakly developed here, more strongly, and then more strongly developed here. From the qualitative development scale that I gave you for clay soils, we can see that this one is moderately developed. So this is mod. This is strong. This is weak here. This one is not quite as strong. This one is weaker. This one is weaker. And then down here, this one is strong. It's moderately developed, or moderately developed to strong development. If these soils represent 100 to 1,000 years apiece, if we assign them ages, and this represents 5,000 or 6,000 years, we can get a rate of sedimentation. What that means is that we have slow accumulation rates here, and we have fast accumulation rate here. Because the soils are weak, that means that there is faster accumulation. And then we have slow accumulation here. Now, the normal way to get a sediment accumulation rate, of course, is to get a date here and a date here. You divide that by thickness, and so you get the meters, or you divide the thickness by the time span, you get meters per 1,000 years or 100 years, meters per year even, or it's usually centimeters per year actually, because sediments don't come in that fast. What's nice about this is you can see relative changes in sediment accumulation. You can see the rhythm of sedimentary accumulation. Very commonly, we find when we measure paleosol sequences, they turn out like this. They turn out to be aging upwards. In other words, the older soils are at the top of a sequence. They also turn out to be draining upwards. In other words, the soils that are higher in the stack are better drained than the soils that are lower in the stack. And quite often they also turn out to be drying upwards. In other words, the soils that are higher in the stack are normally in a slightly more acidic climate than the soils lower in the stack. What these are telling us about is subtle changes in climate, in drainage, and in rate of accumulation of these individual sequences. So there's a sequence boundary here and a sequence boundary here. In terms of sequence stratigraphy, what would give you this kind of a sequence is the ocean regressing here and then transgressing up to here, ponding the sediment influx from a coastal region so that the soils are better developed. These kinds of cycles are commonly tied to transgression and regression in the ocean nearby. And these transgressive and regressive cycles are important for understanding the construction of sedimentary sequences, and in particular for finding oil and gas, which is where this whole sequence stratigraphic idea was invented, because these are good possible reservoirs, these sands, good possible reservoirs of hydrocarbons, and these well-developed soils are good caps that hold the hydrocarbons in. This has some economic significance in the search for hydrocarbons, for oil and gas in sedimentary sequences. Generally speaking, we see an asymmetric pattern like this, a zigzag pattern, where we have a situation where it is you've got a well-developed soil here, then it goes like so, and then up to here, and then it goes down again. This can reflect an incomplete, there's often a hiatus here, an incomplete sequence. Most paleosol sequences of my experience are actually like that. But I did actually find one example in the case of the Himalaya, in the Siwalik group in Pakistan, where the soils formed a kind of very interesting sinusoidal pattern. If we're just plotting soil development now of successive paleosols, and there were many of them, they formed this lovely sinusoidal pattern. This is about 10 meters of sediment, individual paleosols. In this particular area of the world, this was Himalayan outwash. The soils were forming over periods of only about 2,000 or 3,000 years apiece. These sorts of sedimentary patterns are very, very rare, and they often represent Milankovitch cycles. You've probably heard of these before in your geological education. 100,000 years cycle is from orbital eccentricity. The 42,000 year cycle is due to obliquity, or the angle of the Earth tilt in its axis away toward the sun, and 23,000 years is due to precession. In the last ice ages of the last 1.6 million years or so, these cycles have meant the difference between large ice sheets and low sea level, and small ice sheets and high sea level. The Sawalich sequence seems to reflect the waxing and waning of these variables on these kinds of a timescale. And we have an independent paleomagnetic and also some radiometric dates for the Sawalich to bear that out. Most sequences of paleosols, however, show this kind of abrupt pattern with hiatuses, reflecting a change in base level. So the time for formation of paleosols is useful for reconstructing sedimentary history in detail, and particularly for informing this rather important area of sedimentology called sequence stratigraphy, which is widely used to figure out the way in which sedimentary packages were put together, and is of value in the search for hydrocarbons and other soil resources. So that's time for formation of soils, and that'll do it for today. Thanks for your attention.